Walaikum sir.
Well, so you have finished wave optics also. Huh? Now the last part, second last part of your syllabus, and that is modern physics. So in modern physics, you have three topics. One is this photoelectric effect and de Broglie hypothesis, another is atom and nuclei. These three topics are there. Now these topics are not new. You have already done these topics in your class 11th chemistry. In chemistry, there was this de Broglie hypothesis, right?
Yes, sir.
You
Yes,
did
sir.
Bohr's model.
Yes, sir,
You
we
did
did.
Rutherford model in 11th. And I hope you all also done fission and fusion type things. No, that is new. That was not there in chemistry syllabus. Only this fission, fusion, and mass defect, that's the new thing. Everything else is you have already done in your class 11th chemistry syllabus. This is the easiest part of your syllabus. You don't get very lengthy calculations. There is no vectors, no integration, no calculus, nothing. This is the easiest part of your syllabus. So this starts with the so de Broglie hypothesis starts with the concept of dual nature. So this is photoelectric effect. Anyways, we are doing modern physics.
So what is the chapter's name?
See, the branch is modern physics. This modern physics will have three topics. One is dual nature, three chapters basically. Dual nature and photoelectric effect. Photoelectric effect. Then you have another chapter by the name of atom. Now this whole atom is repetition of class 11th chemistry syllabus. And then you have nuclei. There are few new topics in nuclei, but it's very, very small. So this is the entire modern physics. And this is the most scoring portion of your syllabus. See, ray optics is scoring. Wave optics, you can get some tough questions from wave optics, but modern physics and electronics are very, very scoring topics. So we'll start with this dual nature and photoelectric. Photoelectric effect, this is the name of the chapter, and dual nature. So whatever you have around you, you can divide all those things into two categories. That's either a wave or a particle. Whatever you have around you can be divided into two parts. It's either a wave or a particle. Like this pen is a particle, sound is a wave. So you can classify everything into two broad categories. It's either a particle or a wave. But there are certain theories which says that particle and wave characteristics are not independent. Everything have both the characteristics. So if you go to this theory, then if you talk about light, what is light? It's a particle or a wave. So light shows both the type of characteristics. It shows particle characteristics as well as wave characteristics. When you say that light is a wave, it shows wave characteristics also. Then the experimental evidence in the support of the wave theory of light are, we did interference. Interference is possible only for waves. We did diffraction. This is also a wave theory. This is possible only for a wave. Ray optics, reflection, refraction, that can be explained using both wave theory as well as particle theory. So I'm not writing it here. So this particularly interference and diffraction shows that light is a wave. Then light may also behave as a particle. So the phenomena which support the wave theory of light, particle theory of light, one of them is photoelectric effect. Photoelectric. So photoelectric effect is the phenomena which supports the particle theory, and interference and diffraction, these phenomena supports the wave theory of light. So we have already done everything related to the wave theory. Now we will come to particle theory. So while doing photoelectric effect, we will consider light as a stream of particles. A stream of particles is coming. So we start particle theory with the concept of, we will do some basic, just note it down. Then we'll do some basic physics first. Written?
Yes, sir.
Okay. So we starts this photoelectric effect with the concept of Planck's quantum theory. Planck's quantum theory. See, we say these all topics as this branch as modern physics because whatever the topics that you will study in this branch were introduced in 18th century, early 18th century or late 18th century. But all other topics that we did in the entire year, those topics were introduced in 17th centuries or as far as 16th century. So that's in that way, this is modern physics. The next is Planck's quantum theory. So the Planck quantum theory says that if light is coming from a source, then that light does not behave like a wave, is behave like as packets of energy. So Planck says if light is coming from a source, then it's not continuous. The light coming from the source have packets of energy. So these packets comes one by one. So it's against the usual belief that light waves are continuous. Light waves are not continuous. Light waves are a stream of particles, and those particles are coming one by one. The first particle came, then the second particle came, the third particle came. These packets of energy were known as quanta. So Planck's named those packets as quanta, and nowadays you call them as photons. So you can say photons are the particles of light. So if you're saying light is coming from a bulb, that means photons are coming from a bulb. So it's not a continuous radiation. These are packets which are coming one by one. But these packets are traveling with a very high speed, which is speed of light. That's why it seems continuous, but light is not continuous. It's quantized. One by one, the packets are coming. That's Planck quantum theory. So if nu is the frequency of each photon, is the frequency of photon, then you can write energy of photon as, you can say that energy of photon E is equal to h, where h is the Planck constant. And the value of Planck constant is, it's 6.626, sorry, 6.626 into 10 raised to the power minus 34 joule seconds. That's Planck constant. 6.626 into 10 raised power minus 34 joule seconds. So this is Planck's quantum theory, that the radiation which is coming from a source consists of stream of particles, or that consists of packets of energy. Each packet have a definite energy. The energy of each packet is h nu. They are known as quanta. You can call them as photons. That's Planck's quantum theory. So this theory supports the particle nature of light. It says that light consists of stream of particles. You can say that those particles are photons. So in the language of a very layman, you can say that photons are particles of light. So when we say that light exists in particle picture, light is coming. So in particle picture, we say that photons are coming. Particles of light. So that's the first theory, Planck's quantum theory, which says that energy depends upon frequency. Second theory. Then you have a special theory of relativity. Not special theory of relativity. Einstein's mass energy equals. Einstein mass energy equals. So the mass energy equivalence of Einstein says that mass can be converted into energy or energy can be converted into mass. So mass and energy are not two independent terms. They depend upon each other. So if m is the mass of body, or you can say that m is the mass of photon, E is the energy of photon, then you can relate this E and M and you can write this as E is equal to mc square. That's Einstein's mass energy equivalence. E is equal to mc square. So that mass energy equivalence says that mass can be converted into energy. So if m mass get converted into energy, the energy is mc square. That's mass energy equivalence. So when we study modern physics, energy may not be conserved. Means energy can be converted into mass. Mass may not be conserved. It may be possible that some mass get destroyed. But when mass get destroyed, equivalent amount of energy is created. So if m mass is destroyed, then E amount of energy is created. So that's energy, Einstein's mass energy equivalence. Okay, now in this mass energy equivalence, you can calculate the mass of photon also. So there is one statement which says rest mass of photon is 0. The rest mass of photon is 0. So mass, up to now we have studied that mass is constant, but mass can vary with speed. Every particle have two types of masses. One is the rest mass. This rest mass is the mass of the particle when they are at rest. Another can be the moving mass, means mass of the particles when they are in motion. So we can say that rest mass of photon is 0. But when photons move with some speed, then they gain some mass, and mass of photon at speed c. So when photons are moving at a speed c, then they gain some mass. That mass can be calculated using these equations 1 and equation. See, both the equations are giving the energy of photon. One is in terms of frequency, another is in terms of mass. So when you equate 1 and 2, you can write that mc square is equal to h. Or you can say that mass of the photon is it's h nu over c square. So this is the mass of photon when they are moving at a speed c. But if your photons are at rest, then their rest mass is 0. We usually represent rest mass in this way. M naught is equal to 0. Rest mass is 0. So you can say that mass of photon is directly proportional to frequency. The next type of question In the next question, he can ask about the momentum of photon. If you want to calculate the momentum of photon. Momentum of photon. See, momentum of anything is mass into velocity. Photons are moving with mass m. They have mass m and their speed is c. So mc is the photon momentum. M is h nu by c square. So you can write this as h nu over c square multiplied by c. C and square gets cancelled out. This is h nu by c. So the momentum of photon is h nu by c. These three topics are general modern physics. We have not yet started photoelectric effect. Your syllabus starts with photoelectric effect, but to understand modern physics, you should know these theories: Planck's quantum theory. You should know energy, Einstein's mass energy equivalence, and you should know that the rest mass of the photon is zero. But when photons move, they gain some mass, and that mass is h nu by c square. You should remember this relation that mass is directly proportional to frequency. This nu is frequency. If you look at previous year's questions, there are few questions based on this relation that arrange photons in the order of increasing mass. And that's the momentum. Start writing. And tell me if you have any doubt, Shahzada, Faisal, any doubt, any issue?
No, sir.
Mariam?
No, sir.
This one is the scoring topic. Easiest part of the syllabus, modern physics and electronics. Yes, no. The mass of an object increases with speed, not just speed of light, but at any speed. This is how mass varies with speed. M is m naught over root over 1 minus v square over c square. This is the rest mass, and this is the mass of the body when it's moving with the speed. So mass increases with speed. As you increase the speed of the body, its mass keep on. But in day-to-day life, our speed is very small. Like, see, if you look at this vector, you're dividing v square by c square. C is speed of light, 3 into 10 is power 8. So in day-to-day life, this increment is negligible. If you don't consider this increment in day-to-day life. But if the particle is moving at a very high speed, some comparable to the speed of light, if speed is 10% of the speed of light or 50% of the speed of light, the speed is very high. At that speed, the change in mass is significant. In our day-to-day life also, mass increase with speed, but the change is not very significant. Yes, no, tell me.
Okay, sir.
That's Einstein's special theory of relativity, STR. Sanya, written? Sure. There are few more concepts that one should know before starting photoelectric effect. And that is the concept of energy of photon and the intensity of photon. You should understand the difference between the energy of photon and intensity of photon. But before starting this, just a simple question. Can you compare the mass of red and blue photon? Compare mass of red and blue photon. Yes. Which one is heavier, or they have same? They should have same mass.
Blue one is heavier
Why blue one? Why blue one is heavier?
because its frequency is higher.
See, mass is directly proportional to frequency. The frequency of blue color is greater than the frequency of red color. It's greater than the frequency of red color. So you can say that mass of the blue color photon is greater than the mass of red color. So mass varies with frequency. If you have to compare the masses of photons of two different color, then just compare their frequencies. The relation of frequencies and masses is same. The next is energy. Just note it down. The next is energy. See, the energy of photon, energy of photon. The energy of photon depends upon its frequency. Yes, Anya. Energy of photon depends upon its frequency. Yes, Noor. Sure. Energy of photon depends upon its frequency. Greater the frequency, greater would be the energy. So energy of photon is proportional to frequency. Frequency of light. It is independent of the number of photons. Energy is independent of the number of photons. So if you increase the number of photons, then energy will not increase. Energy will increase only if you increase the frequency. It is independent of number of photons. Independent of number of photons. So that's one thing. Energy of photon does not depends upon number of photons. It depends only on the frequency. So if you change frequency of light, then the then the energy of photon will change. It's independent of number of photons. Then another term that you will use in photoelectric effect is intensity of photon. So when we say intensity of photon means number of photons per unit area per unit time. So intensity means number of photon per unit area per unit time. That's intensity. Intensity depends upon the power of the bulb. Like if you increase the power of the bulb, you have a bulb of 100 watt and a bulb of 1000 watt. So the intensity of light coming from the 1000 watt bulb is greater than the light coming from the 100 watt bulb. It depends on power of source. Power of source. Power of source means intensity of light from 1000 watt bulb, 1000 watt bulb, 1000 watt bulb is more than 100 watt. And one more thing, intensity is independent of frequency. It will not change on changing frequency. It is independent of frequency. If it is independent of frequency. See, in photoelectric effect, now you have graphs. Majority of questions that you get on photoelectric effect are graphical questions. To solve those graphical questions, you should have a very clear-cut idea of what this intensity means and what does frequency means. What happened when we change frequency and what happened when we change intensity. All questions that you will get on photoelectric effect are mostly graphical. So it is independent of frequency. It depends only over the power of the source. Note it down. We'll do some questions on it. Any doubt, Faisal?
No, sir.
Written? So you have two bulbs, 100 watt bulb of red color, and you have another 100 watt bulb of blue color. So you have two types of bulb, one of red color, another of blue color. Yes, Amalia, can you compare the energy of light photons coming from these two bulbs? See, the power is same. Both bulbs are of 100 watt. Can you compare the energy of photon from the two bulbs? The energy of photon from the two bulbs will be same, or they have different values. If they have different, then which one have greater energy and which one have lesser energy? Yes, Amalia. Okay. Mariam, can you decide out of these two bulbs which have higher energy or they have same energies? Mariam,
So the red bulb.
red bulb will have lower or higher energy?
Higher.
Higher energy. Abdullah,
So lower. Red one will have lower.
see the energy, Mariam, energy depends upon frequency. Yeah? Frequency of blue color is greater than frequency of red color. Say red color have higher wavelength but smaller frequency. So frequency of blue color is less than the frequency of red color. Blue color is less than the frequency of red color. So the energy of light coming from blue color is less than the energy of light coming from the red
So frequency of blue was more, right?
color. Sorry, yes. Sorry. Frequency of blue color is greater than red color. So energy of light coming from blue bulb is greater than the red light. So blue photons will have large energy. Amalia, another question. If I change the power, like if one bulb is of 100 watt, this have light of red color, or instead of 100 I make it at 1000, and another bulb is of same wattage 100 and it emits blue light. Can you compare their energies now? Energies will remain same or it will change? Malia, if I change the power of the bulb, then intense energy will remain same or it will change?
It will change.
It will change. Okay. Sania, what do you think? If I change the power of the bulb, then the energy of photons coming from the bulb will change or it will remain same? Good. Malia, energy will remain same. See, energy is independent of number of photons. Energy depends only over frequency. If you're not changing frequency, then energy will not change. Energy is independent of power of bulb. It's independent of power of bulb. It's independent of power of bulb. So if you change power of bulb, then energy of photon will not change. This is the particle theory. So if you take a red bulb, you take a red bulb of 10 watt and you take a red bulb of 1000 watt. Both the photons coming from both the bulbs will have same energy. But on changing the power of the bulb, number of photons will change. This will emit more photons than 100. Intensity will change. Bulb of 1000 watt will emit more photons than the bulb of 100. Is it clear, everyone? Faisal, Shahzada? See, all graph that
Yes, sir.
get on photoelectric effect will use these concepts. And the best thing about this topic is now the next 3 chapters are totally independent from the entire syllabus. Does not matter that you have studied optics or not. These next 3 chapters, like photoelectric effect, atom, nuclear, radioactivity, it does not depend upon the previous chapters. They're totally independent. Just note it down. These 2 things. Amalia, is it clear now?
Yes, sir.
The next is the concept of unit of energy. What is the SI unit of energy, Shahzada? Yes, Shahzada. What is
Joule.
it? Joule. Yes, the SI unit of energy is Joule. But in modern physics, throughout modern physics, we will not use Joule. We will use electron volt. So we'll use EV, electron. This unit of energy we will use. 1 joule is very large unit to study modern physics. Electron. 1 electron volt is 1.6 into 10 raised to the power minus 90 joule. So this is the relation between electron volt and joule. 1 electron volt is this much of joule. Another unit that we will use is MEV, mega electron. Mega electron volt we will use. 1 mega electron volt is 10 raised to the power 6 electron. So this is the unit of energy that we will be using. Electron volt and mega electron. Then the next definition is work function. Work function. Work function is the minimum energy required. Minimum energy required to eject electrons from the metal surface. To eject electrons from the metal surface. So if you want to eject electrons from the metal surface, then you have to supply some energy to the metal, and that is known as wave work function. Say this is a metal surface. It is a metal surface. You want to eject electrons from this metal surface. You want to eject this electron from the metal surface. This electron from the metal surface. So to eject electrons from the metal surface, you will provide some energy to the electrons. Basically, electrons are not free. These electrons of the metal surface are not free. They are bounded by metal surface. So the minimum energy that can remove these electrons from the metal surface is work function. That's the minimum energy that can remove electrons from the metal surface. That's work function. Cesium have minimum work function. You should remember this thing. Cesium have minimum value of work function. Minimum work function. Work function of the cesium is the minimum value of work function. Note it down. Written?
Yes, sir.
See, all these topics are general topics. You will use these topics in photoelectric effect. You will use them in atom as well as in nuclei. You can't do modern physics unless you know this much of physics. Written?
Yes, sir.
No, Abdullah, just last topic.
Yeah.
The unit of mass that we use in modern physics is not kg. Usually, mass is given in AMU, atomic mass. Atomic mass unit. One atomic mass unit, one AMU, is 1.67 into 10 raised to the power minus 9, not minus 90, minus 27 kg. This is how you convert one AMU into kg. Then there is a question. Convert mass of 1 AMU into energy. So Faisal, which relation you will use to convert mass into energy? Which relation can convert mass into energy?
E is equals to mc square.
E is equal to mc square. See, your mass is 1 AMU, so I'll convert this into kg. So this is 1.67 into 10 raised to the power minus 27 multiplied by c square, which is 3 into 10 raised to the power 8 square. If you want to convert this in electron volt, just divide it by 1.6 into 10 raised to the power minus 90. This is how you will convert this in electron volt. If you want to convert this into mega, then divide it by 6. So when you do all these calculations, you get 931.5 mega electron. So if you convert 1 AMU of mass into energy, then you get energy of 931.5. So you should remember this result. 1 AMU of mass will give this much of energy. If you destroy mass corresponding to 1 AMU, then you will get energy equal to 931.5 mega electron. You have to remember this result. We'll use this result in all calculations. Note it down. Yes, written. So that's the last topic. We'll stop here. The next class we will take 1.5 hours only to finish photoelectric effect. The next class will finish this chapter. Okay, so let's stop here. Love is continue the next class. Okay.